What's up, YouTube? So today we're going to be talking about balancing redox reactions. Now, typically these type of problems like to pop up on the FRQ section of the AP Chemistry exam in May. Also, these type of problems can be given in certain unit tests in your AP Chemistry class. So basically what we're going to do is we're going to have a step-by-step approach on how we can kind of attempt these type of problems and solve them with relative ease. So without further ado, let's get started. So here we have a redox reaction, and ultimately what they want us to do is they want us to balance this reaction out. So the first step, step one, when it comes to balancing a redox reaction, is we have to dissociate all the compounds that are soluble in water. The reason why we want to dissociate all the compounds that are soluble in water is because we want to find out what the spectator ions are. What spectator ions are certain ions that are both found on the reactant side and the product side that don't really do anything in the reaction. They just stay there and they don't really react with anything. They're just floating around. And they're not really essential when it comes to getting an ultimate balanced reaction of a redox reaction. So that's what we're going to do first. We're going to find all the compounds that are soluble in water. So this, when we come to attempting these type of problems, we do have to have prior knowledge of our solubility rules. So if you're not that familiar with the solubility rules, or if you need to refresh, there is a previous unit and there are videos that will kind of go over the solubility rules. So I do encourage you to check out those videos. A link will be down below in the description. So I'm going to continue this video with the assumption that you guys know your solubility rules, and I will do this first step pretty quickly, but I will also explain why I'm dissociating what I'm dissociating. So the first thing that I'm dissociating is the manganese chloride. The reason why I'm dissociating it is because chloride is a halogen, and halogens are soluble in water unless they are attached to a mercury or a lead or a silver. And seeing that manganese is none of those three, I know that manganese chloride is soluble in water. Okay, so I'm going to write that out, and I'll continue it in green. So manganese is going to be a 2+ because we need 2 chlorine ions, which is a -1 charge. If we need 2 chlorine ions to make this total compound neutral, I know that manganese is a 2+ charge, and I know that chlorine will be a minus charge, okay, because it's a halogen. My diatomic iodine, I'm not going to dissociate. It doesn't dissociate in water. It's not one of those things that is soluble in water. So I'm not going to worry about it. I'm going to keep it as is. The potassium chloride. The potassium chloride will dissociate because we have a group 1 metal and we also have a halogen. So that'll dissociate, and water is not soluble in itself, so water will stay as is. Now we have potassium permanganate. Potassium permanganate will dissociate because there is a group 1 metal, which is the potassium. And I know it's a K+ and a permanganate, which is a minus charge to, balance these two out. I know that my potassium iodide will also dissociate because of this group 1 metal. And I know that my strong acid here, my hydrochloric acid, will also dissociate because of this halogen. Okay, and also typically acids do typically dissociate in redox reactions. Okay, so this is my total dissociated reaction. This is where I dissociate all the compounds that dissociate, and I write them all out. Okay. And this is also commonly called in chemistry the net ionic equation. Okay, so now that I have this net ionic equation, I can cancel out certain spectator ions. Okay, so spectator ions, as I already described, are found both on the reactants and the product side. So these ions don't really do anything to the reaction, or don't do anything in the reaction. So what ions are found on both sides? Well, I can see a chlorine on both sides, and excuse me, I need to put a minus sign there. But I see chlorines on both sides. So I'm going to cancel those guys out. So chlorines get canceled out. There's another chlorine here. And also, it doesn't matter the amount of chlorine on both sides. As long as they're present on both sides, you can cancel all of those ions away. So even though there are 2 chlorines here and only 1 chlorine there, it doesn't mean that we can only cancel out 1 chlorine. No, we cancel out all of the chlorines, okay? So we cancel out all the chlorines because they are spectator ions. Another ion that is a spectator ion is the potassium over here. I can cancel out all the potassiums that I find. What is the next one that I can cancel out? Really nothing else. The manganese, the diatomic iodine, the water, all of them are pretty unique. Okay, so these are the essential reactants and the essential products that are mainly going to be reacting with each other. Okay, so I'm going to kind of bring this down. So step number 2 when it comes to balancing a redox reaction is bringing down everything you didn't cancel out, or bringing down everything you didn't identify as a spectator ion. I'm going to rewrite this number 2. All right. So I'm going to bring down my manganese, and I'm going to write it out in a different color. Write out all the essential ones in a different color. So I have a manganese 2+, I have a diatomic iodine, and I do have some water. Okay, and I have some permanganate that I will use, some iodide, and some H+ ions. Okay, so now what we have to identify is we have to identify the two essential reactants and products that are mainly changing within this reaction, okay? Remember, this is a redox reaction, meaning one of these guys has to be getting reduced and one of them has to be getting oxidized. Because we're mainly focusing on the flow of electrons within the reactants and the products, we should know that if you gain an electron, you're being reduced, and if you lose an electron, you're being oxidized, okay? That is a common rule when it comes to redox reactions. So the 2 main species that I want to examine here are the manganese, okay? Because I do see a change in the manganese. So I'm going to focus the Mn, the manganese 2+, and the permanganate. I'm going to focus on this reaction, and I'm also going to focus on a second reaction, which is the diatomic iodine and the iodide ion. Okay, so I'm going to focus on these 2 reactions because I do see a major change in those reactions. Okay, so I identified my 2 reactions. So step 2 is bringing down all the essential reactants and products and picking out 2 reactions. Okay, 2 reactions. This is one reaction in white, and this is another reaction in red. And I'm going to pick those 2 reactions as my focus, okay? So step number 3 is analyzing my focused reactions. Okay, so I'll do each one in a different color. I'll do the manganese in orange. So Mn2+ turns into permanganate. Okay. So let me first balance this small reaction out, okay? This is a focused reaction, so I'm going to balance this guy out first. All right, so basically what I'm going to do is I'm going to see, what can I do to balance this out? Well, I do have 1 manganese here, and I have another manganese here, but wait, I have 4 oxygens on this side, and I have 0 oxygens on this side, so what can I do? Well, I can add, and this is a rule that you have to know when it comes to redox reactions. If you want to add oxygens, you can add water molecules to the system. Okay, so we're going to add some water. You can add some water to the reaction to balance out these oxygens. Now, we need 4 oxygens, so I need to add a proportion of 4 water molecules. Okay, in proportion to the 1 and 1, I have to add 4 water molecules. Alright, so when I add these 4 water molecules, I get 4 oxygens, 1 manganese, 1 manganese. But wait, I also have 8 hydrogens, and I need to have 8 hydrogens on the product side. So how can I do that? Well, I can just simply add 8H plus. Okay? And you're like, whoa, how can you just add random stuff that you need? Well, there are rules when it comes to redox reactions. The certain things that you can add to help you balance these reactions out are the first ones that you can add, and I'll write this out somewhere else. The first thing that you can add is you can add H2O, and this can help you balance out the oxygens. The second thing you can add is H plus ions, and the third things you can add are hydroxide ions. But other than that, you can't add anything else. So just keep these three things in mind. Okay, you can add these guys when it comes to balancing certain reactions. So now that I'm done balancing these guys out in terms of the specific elements, I have to balance out their charges, because that's the second thing that's not balanced. So here we don't have any charge, but we do have a 2+ charge on the manganese. So we have a total charge on the reactant side of 2+. On the product side, we have a 1- charge, and we have a 8+ charge because there's 8 H+ molecules. So that makes a total of a 7+ charge. So the second rule that we have to understand is when it comes to balancing out charges, you can add electrons. Okay, so the last and final thing you can add are electrons to help you balance out equations. So which side would we want to add electrons to, or which side do we want to decrease the charge of? Well, the side that we want to decrease the charge of is obviously this side, because it's a 7+ charge. It's a much higher charge. And we want to make this ultimately 2+ and 2+ to balance out the charges. So we have to add 5 electrons to the product side to make this total charge 2+ and this total charge 2+. So now we have 8 hydrogens, 8 hydrogens, 1 manganese, 4 oxygens, and we have a total charge of +2, and we have -1 plus 8 is 7+, minus 5 is +2. Okay, so we balanced out this whole reaction. Now what we have to do is we have to identify, is this reaction being reduced, or is this reaction being oxidized? So when we look at this reaction, if you have to add electrons to the reactant side, it is being reduced. Okay? If you add electrons to the reactant side, it is being reduced. Okay? Now, in this reaction, we're adding electrons to the product side. So that means that it's being oxidized. Okay? And you can think about it pretty logically, okay? If you're going to be adding electrons to the reactant side, you know that the reactants are essentially gaining electrons, okay? And if they're gaining electrons, they're going to be reduced. But here, they're not gaining electrons. The products are gaining electrons. So they're going to be oxidized, okay? So if it's in the products, it's being oxidized. If it's in the reactants, it's being reduced. Okay, so now that we essentially balance this reaction out, we can move on to the second reaction in focus, which is with the iodines. So I'm going to write out the second reaction in blue. Okay, so we have some diatomic iodine and we have some I-. Okay, and we want to first balance out these charges. So the first thing we have to do is we have to see, okay, we have 2 iodines here and we only have 1 over here, so we have to make this 2. All right, now the second thing we have to do is there's no oxygens here and we don't have to balance out any hydrogens, so we don't have to worry about 1 and 2 or 3. Now we have to balance out the charges. So on this side we have a charge of 0. Okay, and on this side we have a charge of 2-. So which one is a higher charge? Okay, I think that's the proper word, a higher charge. Alright, so the one that is a higher charge is obviously the 0, because the 2- is negative. Okay, so we have to add electrons to the side that is of higher value. And if we add 2 electrons here, we get a total charge of 2- and a total charge of 2-. So we have balanced out this reaction. now that we see that we have to add electrons to the reactant side, we know that this guy is being reduced. Okay, so the reactions where I2 is becoming I minus is being reduced. Okay, and also that makes some logical sense, because we have a molecule that is of zero charge becoming a negative charge, meaning it's gaining electrons. So this should be reduced. It's logical for this to be reduced. Also, this one, and essentially that's the logic behind it. Okay, so now that we understand how to balance out the reactions, and we understand also that depending on where we add the electrons, we can identify it either as oxidized or reduced, we can take this information and balance the total reaction out. So now what I'm going to do is, what I want to do ultimately is I want to cancel out these electrons, okay? I want to keep everything else essentially the same. I don't want to change everything else drastically, but I want to balance out these electrons. I want to cancel them out. Okay, so how I do that is, you can kind of, for the mathy people out there, you can kind of look at it as like a system of equations, all right? You have to multiply both of these reactions by a certain number to allow these electrons to cancel out, because we don't really need electrons in the final balanced equation, right? So we want to get rid of them. So if we multiply the top by 2 and the bottom by 5, we would get a factor of 10 electrons on both reactions, and we can cancel them out because we have electrons on the reactant side and electrons on the product side, so we can cancel them out. So if we do this, we have to multiply the whole reaction by 2. And if we multiply this whole reaction by 5, we have to make sure we carry that on to all of these species. So this becomes 8, because 4 times 2 is 8. This becomes 2. This also becomes 2. This becomes 16, and this becomes 10. This becomes 10, this becomes 5, and this becomes 10. All right, and all I simply did was I multiplied the moles that were already in the reactions to the ultimate number that I'm multiplying in order to balance out these electrons. So now that I have 10 electrons on both sides, I can cancel them out, because one is on a reactant side and one is on the product side. So now I no longer have any electrons. I cancel those out. So everything else that I'm left with is going to be my balanced reaction. Okay, so I'm left with some H2O, 8 H2O. I'm left with 2 manganese ions. I'm also left with 5 diatomic iodines. I'm left with 2 permanganates. I'm left with 16 H pluses, and I'm left with 10 I minuses, iodine ions. So now we have to write out the final reaction. So the final balanced reaction is 8 H2O plus 2 Mn2 plus 5 I2. Okay, and I'm not writing out the electrons because I canceled them out. All right, yields 2 permanganates, 16 H pluses, hydrogen ions, and also 10 iodides, or 10 iodine ions. Excuse me. So now I'm just going to double check. Do I need to simplify it anymore? Are there any common elements or compounds that I can further simplify? No, I don't see anything further simplified. So this would be my final balanced reaction. Now there is a way that you can double check your answer, and that is if the overall charge of the reactants equals the overall charge of the products. Okay, so here we have 0 charge plus 2 plus, which is a 4 plus charge, plus 5 times 0, because the I2 is of 0 charge, it's not an ion, so plus 0, so that yields a full charge, ultimate charge of 4 plus. And we have 2 minus over here, so 2 minus, so minus 2 plus 16, minus 10, because it's a 10 minus charge. So here we have a minus 2 plus 16 is plus 14. Plus 14 minus 10 is a plus 4 charge. So plus 4, the overall charges of the reactants and the products balance out. So we know that this reaction, this reaction is going to be our balanced redox reaction. Alright, thank you for tuning in for this video. Please leave any comments in the comment section down below, and also please leave a subscribe. I hope this video has been informational. Thank you.